Welcome, my dear students. This next class, last class, we discussed about the uh, eigenvalues and eigenvectors properties, and we show that if we have a lambda 1, lambda 2, lambda n are the distinct eigenvalues, and v1, v2, vn are the eigenvectors corresponding to the distinct eigenvalues lambda 1, lambda 2, lambda n, then these eigenvectors are linearly independent. And then also we show that if we have a lambda is an eigenvalue of a, then lambda to the power k is an eigenvalue of a to the power k in this form. Now in this case we have to discuss about the how to using this linearly eigenvalues and eigenvectors to diagonalize the matrix. Okay, so we start with we let A be n by n matrices, and assume that n has a distinct eigenvalues lambda 1, lambda 2 corresponding to the eigenvectors x1, x2, xn. Then we can say that we can write a because all these things. So a of x1 is the same as a lambda 1 x1, and this can be written in the form of x per into lambda 1 because lambda is a lambda 1 is a constant. We can write into this form. Similarly, x2 is equal to this 4, and xn we write into this form. Now you can see this is are the a1, a2, a this is nothing but is equal to x1, x2 are the eigenvectors. So this we can write this as a matrix, as a column of the matrix. This is the one of the column of the matrix. This is the second column of the matrix. This is the third of the column. Then similarly we can write these are the column vectors of a matrix. Now if we just take a x1, x2, xn, that's because we have to write this form. So we can a into take a is a whole out, a can become the matrix into this, and then we can write this a of x1, x2, xn, and here is coming this. Now you just see this is the matrix is nothing but is equal to, we can write this is the sum matrix P, and this is the this is matrix you have a we have denoted this is a P, so we can write this is equal to P and D. This is a diagonal matrix because all the elements of a diagonal except the diagonal elements, all other elements are 0 here. So that means we can clearly say that this is you have a P. So we can say that this P means we have to find what is this P, and then we can just say that because A is all the vectors are this x1, x2, xn are linearly independent. Because of the theorem we have to prove that. This means if we have x1, x2, xn are the eigenvectors corresponding to the distinct eigenvalues lambda 1, lambda 2, lambda n. So this means we can say that these vectors are linearly independent. So clearly if these vectors are linearly independent, so where P is this form and D is equal to, we have to denote it as this form. So this can be written as this is a P over, and this is we have to denote it as a D, and this is a diagonal matrix, and this means you know that the diagonal matrix always these are the lambda 1, lambda 2, lambda n are the eigenvalues by the, if we have any triangular matrix, either upper triangular matrix, lower triangular matrix, or the diagonal matrix, we have always the diagonal elements are the eigenvalues of a such a matrix D. So this means since A has a n distinct eigenvalues, the eigenvectors a1, a2 are linearly independent. Therefore the matrix P which formed the eigenvector is not singular because determinant of a P is not equal to 0, and there exists a inverse matrix P. So this means is a non-singular matrix. So that means there exists a inverse, and we can say the P inverse. So this means we have to multiply the P inverse from the both side. From this we can say that P inverse AP is equal to P inverse D. Now we just say that P inverse P is nothing but is equal to is identity matrix. So we can say that P into written in the form of a D. So D can be written in the form of a P inverse AP. So this we can say that any diagonal matrix D can be written as a P inverse AP. Then P is what? P is nothing but is equal to is a column vectors of a corresponding eigenvectors of a this. So this means D we can just calculate the diagonal of a diagonalization of a matrix. We can write find eigenvectors, and eigenvectors can be written in the form of a the columns of a this, and then we can say that take a inverse of a this if we have multiplied this inverse by the matrix P, or we can say that any matrix A can be written as a P, D and P inverse. So this is also we can write into this form. So we can say that now first definition about the before diagonalization. We can say that these two matrices are similar. If we have a and B are the square matrices, We say that B is similar to A if there exists A as invertible matrix P such that B can be written as a P inverse AP. So if we can write like this, we have to just say that if a matrix A in place of this D diagonal matrix, we have to write as a matrix B can be written as a P inverse AP form. Then we can say that this matrix, we can say that matrix this is A and B. B is similar to A, or we can say the vice versa. We can say that A can be written in the form of a P, A and P inverse. Then we can say that this is B. So A can be written as a P, A, B inverse, then A is similar to B, vice versa, this way. So this way we can say, we can write the similar matrices. Okay, so diagonalization, I just said that an n by n matrix is said to be diagonalizable if there exists a non-similar matrix P and the diagonal matrix D such that P inverse A, P can be written in the form of a D, where P, we say that P is diagonalized A because we can say that A is similar to D, or we can say that D is similar to A, and we can also say that this P is diagonalized this matrix A. Okay, so this is the definition for the diagonalizable. Now we have an example. We have a, suppose we have a is equal to, we have a this, so we can first we write the find the eigenvalues of this example. So we can, starting from the diagonalization, first is a minus lambda I. So this can be is equal to 0. We can write in the form of a minus lambda 0 minus 2. You have a 1. 2 minus lambda 1, and then you have a 1 0 3 minus lambda, this is equal to 0. So we can write minus lambda times, you can just say that you have a 2 minus lambda 1 0, you have a 3 minus lambda, you have a minus ka 2 times, you have to go into the 1 2 minus lambda when 1 is equal to 0. So this is minus lambda times, you have a 2 minus lambda, you have a 3 minus lambda, and then you have a minus 2 times of a, you have a this is 0, you have a 2 minus lambda. So 2 minus lambda we can throw out common, so you have a minus lambda 3 minus lambda and plus 2, and this is equal to 0. Then we can say that this is equal to 2 minus lambda, and then we can say this is nothing but is equal to, you have a 2 minus lambda, and then this can be written as a, you have a lambda square minus 3 lambda plus 2 is equal to 0. So you have a 2 minus lambda is a one of the root, then can be written in the form of a, you have a 2 minus 2 and lambda minus 1. This is equal to 0. This implies that we can say that lambda is equal to 1 and lambda is equal to 2 comma 2 are the eigenvalues of this clearly. So if this is this, we just take this the form, and then we can just take a eigenvalues of this. So these are the eigenvalues. Now we have to corresponding to lambda is equal to 1, we find the eigenvectors. So we just take a lambda is equal to 1, we have a matrix 1 minus 1 0 minus 2, you have a 1, and then you have a 1 and 0, you have a 1 0 3 minus 1 is equal to 2, and then you have a x y z is equal to, you have a 0 0 0. So this can be written as a minus x minus twice z is equal to 0, you have a x plus y is equal to 0, you have a x plus z is equal to 0. So this means we can say that x plus 2z is equal to 0. So we have a clearly x is equal to, you have a minus ka z minus ka 2z, and y is equal to, you have a we have a y is equal to, you have a minus ka x. So this means we can say that if we take a z is a z is equal to any value, for z is equal to 1, then we can say that x is equal to, you have a minus 2, then y is equal to, you have a minus ka x, so this is equal to 2, and z is equal to, you have a 1. So this means we can say that one of the minus 2 to 1, one of the eigenvector for corresponding minus 1 0 1, and then we can for lambda is equal to 2 is minus 2 1 1, this is are the, and then p2 is equal to, you have a this is equal to, we have a right into this form. For lambda is equal to 2, we have these two vectors we can getting, and lambda is equal to 1, we getting is equal to x is equal to y is equal to minus 2x and so on. So this means we can write into this form. So z is equal to 1, then y is equal to 1, then we have to just say that x is equal to, you have a minus 2z. So p3 is equal to this, means 3 are the this means p is nothing but is equal to, we can say that minus 1 0 1, then 0 1 0, and then we have a minus 2 1 1, this is our P is there. So this means we have a P is equal to this form, because we write the columns of this eigenvectors into the this P. So this is eigenvectors. Now we try to diagonalizing this. So this is this diagonalizing, we have to find the inverse of this. Now inverse of this we can write P into identity matrix and apply the row elementary operation. We can just take a this is equal to P inverse, converting to this form. So I just using this, I just say that P inverse of this is nothing but is equal to P inverse of this. You have a 1 0 2 1 1 1, and then you have a minus 1 0 minus 1. We have to calculating in this way. We have to just transform, because we have to if you just check, you just take a here you take a we have a 1 0 0 0 1 0, then we have to elementary row operation when you apply. So this is multiplied by minus 1, this should be minus 1, and then we have to by this this is 1 0 2, and then you have a 0 1 1, and then 1 0 1, and then we have to just taking into this form. So this can be written in the form of you have a 1 0 2 minus 1 0 0 and 0 1 1, and you have a 0 1 0, then you have a 0 0 1. Now you have to just taking the this 0, and this is again you have a 0. So this minus 1 times of this, so this is equal to this 2 1 minus 1 minus 1, so you have a minus 1, and then you have to just say that this is third one 0, and then you have minus 1 means 1, you have a 0, and then you have a 1 is this thing. Now with the help of this is equal to 0, so last one we have to just multiply it, third one is equal to you have a by this form, the just to be eliminating into this form. So this means we can getting simply into this form by eliminating row operation. Now if we have to multiply it by these two, now you just check what you getting the diagonal elements of this. So clearly we can say that this is the our D, and D is nothing but is equal to, we have to write is a diagonalization. Okay, so now in general there is no preferred order for the columns of a P, since ith diagonal entries of a P inverse A is the eigenvalues of a ith column vector P. So changing the order of the columns of P, just changing the order of the eigenvalues so on the diagonal. So this means again we have to not prefer any particular order of this. We can change the order of the column, then the eigenvalues is also change this order is this thing. So this means we had a P is equal to, we have to just check the change the order of these two, then we have to calculating the P inverse P is equal to this. Now you can see here, if we change the order, then the eigenvalues order is changed. Here we have a 2 2 1, and then you can just say that we have a this is corresponding to 2, and this is corresponding to the eigenvalues for 1. And now what I do just change the this order of this. I shift this is equal to 1 here. So this means this is corresponding to lambda is equal to 1, this is corresponding lambda is equal to 2, lambda is equal to 2. So middle one is this middle one term is coming into this form. So if we have to change the order, then we can clearly say that this way we getting the eigenvalues of this corresponding to the in this form. Okay, so this means just say that now we try to this is not an diagonalizable. This example we just again find the eigenvalues of this. Clearly we can just take a determinant of a minus lambda I characteristic equation, write into this form, and now we just calculating this, we write into this form. Clearly if we have to eliminating from corresponding to this, so you have a lambda minus 1, then you have a going to this, you have a lambda 2 का whole square, then again lambda is equal to 1, and lambda is equal to 2 are the two distinct eigenvalues. We have a lambda is equal to 1 and lambda is equal to 2 are the two distinct eigenvalues. Now corresponding to this we take a, for example, if we take a for lambda is equal to 1 corresponding eigenvector, if we put a lambda is equal to 1, you have a 0 0 0, then you have a minus 1, you have a minus ka 1 0, then you have a 3 minus 5, and you have a minus ka 1, and then you can write the x y z is equal to, you have a 0 0 0, then first row is then you have a minus x minus y is equal to 0, implies that you have a x is equal to minus y, and then you have a 3x minus ka you have a 3x minus ka 5y, and then minus ka z is equal to 0. So you can say z is equal to, you have a the minus ka 3x plus ka 5y, and then you can x is equal to, you have a minus y, so you have minus 3y and plus ka 5y is equal to 8y. Z is equal to like this, and then you can just simply depend one of the variables dependent. So we have a 3 variables, 2 system equations. So one of the variable is a free variables. So just we take a z is equal to, you can say that 8 of a y. If we take a y is equal to 1, and then if we take a y is equal to 1, and then z is equal to 8, and y is equal to minus 1, then clearly this should be a minus. Okay, so this means we can say that this is minus z. So z is equal to, you have a minus ka 8y. If we take a y is equal to minus 1, z is equal to 8, and x is equal to 1. So this is the corresponding to this. Now similarly, if you want to corresponding to lambda is equal to 2, so if 2, then 2 minus 1 is equal to, you have a 1 0 0, then you have a minus 1 0 0, then you have a 3 minus 5, and then you have a 0. Then you can say that x is equal to clearly 0, and then we can say that you have a 3x minus 5y is equal to 0. So you have a y is also 0, then you have a z is an arbitrary vector. So we can say that 0 0 and 1. And then for lambda is equal to 2, we have a just, if we take a find a p, then this p is equal to, you have a 1 minus 1 8, and you have a 0 0 1, and this is not a 3 by 3 matrix. So this in the basis only the total vectors in this. So A is a 3 by 3 matrix, therefore only 2 bases of this vector. So this means A cannot be diagonalizing. So A can diagonalize only, this is the again is a 3 by 3 matrix. So this means we can say clearly say that this matrix cannot be diagonalizable if we have a this thing is happening there. Okay, so now we just state a theorem. This theorem is say that if A is an n by n matrix A is diagonalizable if and only if A has a n linearly independent eigenvectors. Moreover, if D can be written as a P inverse AD, with the D is a diagonal matrix, then the diagonal entries of a D are eigenvalues of A, and the column vectors P are the corresponding eigenvectors. So this means where is this is equal. Now we have to just sketch the proof of this. First, suppose that A has n linearly independent eigenvectors v1, v2, vn, and corresponding eigenvalues lambda 1, lambda 2, lambda n. Now that the eigenvalues may not be distinct. So I just note that these eigenvalues may not be distinct. So we have a let p v1 is equal to, these are the corresponding columns for all these things. We define n by n p matrix p, that is ith column for corresponding to vi. So vi corresponding to v1, corresponding to v2, and so on. Since the columns of v are linearly independent, so the matrix p is invertible, and since ith column of a vectors are the product of a ap, so api is equal to a of vi, and a of vi because is the lambda I vi, so a of pi is equal to, we can say that a of p can be written in the form of a lambda 1. This is lambda 1 vi, so vi may v1, so this can be written as a in the form of a lambda 1 here, just check here, lambda 1 and v1, and v1 we can be putting into this form. So this can be written as a lambda 1 p1 lambda 1 and so on. Similarly, we just write in the form of a lambda 2 v2, and v2 is equal to, again you have a this vector, so we have a second column is lambda 2 and so on, p1 p2 pn. And now you just take if you take a write this matrix in the form of this p11 p12, and this is the column vectors of this p, and this is the nothing but is equal to, you can just take a lambda 1 0 0 and lambda 2 and so on. So this means we can say that this is nothing but is equal to this corresponding to all these things. This is column. Now this can be written in the form of this, then we can just set it into this form and so on. So this means this is the matrix. If a product of these two is equal to this, so clearly we can say that this is a this is D. So this can be written A, or P can be written in the for P of D. Now D is a diagonal matrix where the diagonal entries are eigenvalues of A. So AP is equal to, we have a PD. Now we have a P is invertible, so multiplied by P into we getting the P inverse AP is equal to D. So A matrix is similar to the diagonal matrix and therefore is diagonalizable. So by the definition of a similar matrix, A is similar to this matrix D, and that means D is a diagonalizable. Now converse, we just try to converse. Suppose that A is diagonalizable, and that is a diagonal matrix D, and an matrix P exists such that D can be written as the form of a P inverse AP. Now column vectors of a P we denoted by V1, V2, Vn as above. The diagonal entries of a D by lambda 1, lambda 2 up to lambda n, and since AP is equal to, you have a PD for each I is equal to, we have, so this means AP is equal to PD, and we can say that is nothing but is equal to A is equal to A of Vi. A of Vi is equal to lambda of Vi, where V1, V2, Vn are the eigenvectors of A. Since P is invertible, then the vectors V1, V2, Vn are linearly independent. So this means we can just say that this way we can complete the proof of this theorem. So now let's see. We have to let this example again, one more example, then we have to hence to the characteristic polynomial of A. I just take a, for example, determinant of A, this is equal to, we have this thing. Now we have a just a characteristic lambda is equal to 5 and lambda is equal to 3 are the we have distinct eigenvalues. So we can say that lambda is equal to 5 first. So we have a just is equal to -1, 0, 1. Then you have a 2, 3 and minus 5 is equal to, you have a -2. Then you have a 2. Then you have a 1, 0, 4 minus 5 is equal to -1. And this matrix multiplied by x, y, z. Then you can say that this is the system of equation we can write in the form of a in the form of this is equal to minus ka x and plus ka z is equal to 0. Then you have a 2x minus ka 2y plus ka 2z is equal to 0. Now we just say that we can write in the form of a, you have a, and you have a x minus z is equal to 0. So x is equal to, you have a simply say that one of the variables z, and then if x is equal to z, we substitute here. So we get is equal to, you have a x is equal to z. So 2x 2z minus ka 2y plus ka 2z is equal to 0. So you have a 4z minus ka 2y is equal to 0. So you have a y is equal to, you have a 2z. So if we have a z is equal to taking any value for 1. So we have the first column for corresponding to z is equal to 5. We have a x is equal to z. So z is equal to 1. So x is equal to 1 and y is equal to 2. So this is the corresponding eigenvector in this form. And then we can find the, for lambda is equal to, we have another root is lambda is equal to 3. So if we take lambda is equal to 3, then just you have to 4 minus 3 is equal to 1, and you have a 0, 1, then you have a 2, 0, 2, then you have a 1, 0, 4 minus 3 is equal to, you have a 1. Then you can just say that this can be written in the form of a x plus z is equal to 0, then 2x plus z is equal to 0, then x plus z is equal to 0. So this means we can simply say that x is equal to minus z and y is arbitrary. So we just take a this can be written in the form of x is equal to minus z. So this can be written in the form of a, if we take a z, so x is equal to minus z, so minus 1, 0, you have a 1, and then you have a plus ka y, you have a 0, 1, 0. So this means these are the vectors of eigenvectors for this. So we can say that we write the p is equal to, you have a 1, 2, 1 and minus 1, 0, 1. So this means we can say that we can write into this form, null space, simplify this 1, 2, 2, then we can just say that 0, 1 and minus 1 as 0 this form. You just take I have already explained you into this. So I just here I just take a v lambda is nothing kernel of a minus lambda I. So this is equal to 0. So we have a system equation, this is equal to 0. So x is equal to z. So 1, 2, 2 is a basis for v lambda 1, and then you just previously I just show you so because you have a y is equal to 2z, x is equal to, you have a z, and then you can just simply is equal to this one. Okay, so this means you have a x is equal to, you have a z, x is equal to z, x plus z is equal to 0. So x this is somewhere is I think minus x, sorry, minus x plus z is equal to 0. This should be minus x. So this x is equal to z, and then we have to, from here, if x is equal to z substituted here, so you have a x is equal to z, then 2x is equal to 4z minus 2y is equal to 0, 2z minus y is equal to 0, y is equal to 2z. Okay, so z is equal to, you have a 1, so you have a 1, 1 and 2. This is the correct eigenvector is equal to 1, 2, 1. So this means this is 1, 2, 1, sorry. This should be into this form, is the basis for this, for lambda is equal to this. Now corresponding to this is correct. I already calculate the second one is the same one here minus 1, 0 and 0, 1, 0. So this is the same. Okay, no problem. Then this is the eigenvector, so this should be 1. Okay, so just as they are linearly independent, and the basis for this, construct the eigenvector of A. So this is P is equal to, you can say that this is should be 1, 0 1 0 minus 1 0, and then we can just take a identity inverse, and then we just take into this form product. Then you can say that clearly you getting the this is the form of a diagonal matrix. So just we simplify this the diagonal matrix of this A is a diagonalizable. So this means we just say that this is not diagonalizable. I already just explain you. Okay, now just you know that the this already result we have to prove that we have a, if lambda is an eigenvalue of a corresponding to x and x is the corresponding eigenvector, and lambda to the power k is an eigenvalue of a k, and x is corresponding to eigenvector. This means simply that we can say that AV is equal to, if x is, we take x, so we take ax is a corresponding eigenvector. So Ax is equal to lambda x implies that you have a to the power k x is the same as a to the power kx is equal to same as a lambda to the power kx. Means if a lambda is eigenvalue of a corresponding to eigenvector x, then lambda to the power k is eigenvalue for corresponding to the a to the power k x corresponding to this. So this means we can say that we can calculate the eigenvalues of a power of a matrix. Now we have just this matrix. Now we try to, there is a 2 eigenvalues, lambda is equal to 1 and lambda is equal to 2. We have already just check here. We just in this question we just write lambda is equal to 1 and lambda is equal to 2 are the eigenvalues of here. So clearly, if we try to lambda to the power a to the power 7, that means we can say that if lambda is an eigenvalue for a corresponding to eigenvector x, then by this theorem we can say that a to the power 7 is equal to is the eigenvalue of lambda to the power 7, means 1 to the power 7. So 1 to the power 7 is equal to 1. So 1 lambda is equal to 1, then a to the power 7. Do the same for this. Now same for this, we have to take, if lambda is equal to, you have a 2, then you have, we can say that 2 to the power lambda to the power 7 is equal to 2 to the power 7, and then we have to, I think 128 is there. So this means we can say that lambda to the power 27 128. So we can say that where eigenvector p1 p2 obtained the above example of lambda is equal to 1 and 2, we have these two the eigenvectors. So this means these eigenvector corresponding to lambda is equal to 1, and this lambda to 1 to the power 7, and also this is the eigenvector corresponding to the value to the power 7 is 128. So this means also the eigenvector corresponding to the eigenvalue lambda 1 and lambda 2 is just for a to the power 7. Okay, now I just come to the last of this lecture, computing the power of a matrix. How to compute the power of a matrix? The problem of a computing power of a matrix is greatly simplified when matrix is a diagonalizable. To see why this is so, we suppose that A is a diagonalizable n by n matrix, and P is a diagonalizable A to this. This is P inverse AP is equal to D by the previous section, and then we can say take, suppose squaring the both side, we can P inverse P ka whole square, then we have to getting D square into this form, and then we have to rewrite in the form of a P8 P is equal to P A P inverse, then P inverse, this is a identity, this is identity, this can be written as a P inverse A square P. This can be written in the form of a P inverse A square P. This is also D square. So this means we can say in the same, if we take a square again, so we just take a, if we have a P inverse A P ka whole cube, then we can say that P inverse ka, sorry, P inverse A P ka, we can say that a P ka square, and then we can say that P inverse A P, and this can be written in the form of a P inverse, you have a square and P, and then we can say that P inverse A P, this can be written as a P inverse A, P inverse P is identity, so A cube P. In the similar fashion, we can say that P to the power inverse AK is can be written as a D to the power K. So A to the power K can be written in the form of a P d to the power k P inverse. So this means we can say that P into this into P inverse. So this means we can say that for suppose we have example, we can try to this example write the a to the power 13. So we write the a to the power 13. We have already this problem we have to discuss in the previously here. Just is this the same? Okay, so now just say that. Okay, no, this is a different. I just show you this one, maybe this one. Okay, yes, is possible. No, 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 this one, and then we have a okay, this one, or this one. Okay, this one. This one is the problem. We already show that this is the diagonalizable. So we have to just say that this is clearly diagonalizable. We just try to find the, already we find the P inverse for this is this form, and a D can be written as a this is the this thing. Now we calculate a to the power 13. So a to the power 13 is nothing but a d to the power 13 P a to the power 13, and this a to the power 13 means 2 to the power 13. Then we have to write 1 to the power 13, and this we have to take a 2 to the power 13 and then multiplied by this matrix. We have a look like is this. So this means we can, if we have a matrix is a diagonalizable, then we can easily calculate the any power of a matrix also. If matrix is a diagonalizable, we using the property of a, when a is a lambda is a eigenvalue of a, then lambda to the power k is eigenvalue of a, and if this matrix is a diagonalizable, so this way we can calculate the power of a matrix also. So this I just have to stop this class, and this complete the course of this linear algebra. This is the last lecture for my, and I hope you enjoy this lectures, and if you have a, I welcome you the all the feedbacks you have a, you just whatever you have a feedback, you have to get contact me by the email address. My all these things we have available in the my this course web page. So you have my phone number, all these things. So I think you have enjoyed this course, and you understand everything. Everything is you have a clear. I try to explain whatever this, but I welcome to all of your feedbacks about the course, how to improvement, some improvements needing. So I just need your feedback in this sense. So thank you very much for you for this course.